Okay. All right, so let's kick it off here. We're going to continue to talk about chemical reactions and stoichiometry, but we're going to do so now within the context of solution reactions. Okay, and we're going to illustrate this by introducing a new category of reaction here that's very important in chemistry, what's called an acid-base reaction. Okay, so if we have an acid-base reaction here, I'm going to give an example and let's pick it apart here. One of the most popular go-to acids in the general chemistry laboratory is HCl, what's called hydrochloric acid, and a go-to base is sodium hydroxide. These are two that you will no doubt be using in the lab in your Chem1AL course. Okay? Since we're talking about solution reactions, what should be my state of matter on these two here? Aqueous, right? Absolutely. So solutions, an aqueous solution of acid is mixed with an aqueous solution of base. Okay? And again, the HCl here is our acid. The NaOH is our base. I'll explain how I knew that here in a second. All right, but the products of these reactions here is going to be, what we're going to see is these acid-base reactions are an example of a double displacement reaction. So what I'm going to do is I'm going to swap my hydrogen and my sodium in order to get my products here. Okay, so this is just a special category of what we learned about these double displacement reactions. So if I swap these, my sodium and my hydrogen here, now the sodium is going to be paired with the chlorine, still in solution. But now my hydrogen is going to be paired with that OH. So HOH, what's a more normal way of writing that formula right there with two hydrogens and one oxygen? H2O, right? So these are the products of this reaction here. We say that an acid plus a base will give us some salt and water. Because we're talking about an aqueous solution, right? An aqueous solution is what we get when we take, for example, HCl and we dissolve it in water. If water is being produced, it can't be aqueous in a solution of water, right? So this water that's being produced will get this L designation. It's a liquid that's being produced here. And these acid-base reactions, we're kind of just going to gloss over them, kind of introduce them here at this point. There's something that you will learn about in just about every chemistry course that you study. You're going to revisit them again in Chem 1B. You're going to revisit them again in organic chemistry. They're just a really fundamental type of reaction that happens. It turns out that some of the more complicated reactions usually have little acid-base reactions as steps within them. So they're just ubiquitous through all of chemistry. Your body is doing a million acid-base reactions right now. So we're kind of going to just introduce this here today. Again, we say an acid plus a base gives us salt and water. Okay, so first of all, my acid. How did I know that this is an acid? And again, we'll kind of expand upon this definition, but for right now, how are we spying our acids? Our chemical formula starts with H. As simple as that. There's this hydrogen out front here in our chemical formula. Okay, and again, it's that hydrogen that's swapping places with my metal ion in my base. So how do I know that I have a base here? So a base is an ionic compound with an OH minus ion. So now we have a new polyatomic ion here, what's called the hydroxide ion. Remember, we learned about a few polyatomic ions, the nitrate, the sulfate, the carbonate, the phosphate. Now we got a new one here, hydroxide. Okay? Hydroxide has this formula, OH, and it has a -1 charge associated with it. And it's this special polyatomic ion here because it's a base in our acid-base reaction. right? So I know I have a base if I have an ionic compound. Remember, an ionic compound necessarily has a metal ion and an anion. And my anion specifically is this special polyatomic ion, the OH minus, the hydroxide ion. Okay? So an acid, a chemical formula that starts with hydrogen, plus a base, some ionic compound containing OH, will produce a salt and water. And importantly, in chemistry, when we say salt, we're talking about any ionic compound. In cooking, when you're talking about salt, you're specifically talking about one ionic compound, sodium chloride. That's what cooking salt is. In a chemistry lab, whenever somebody says a salt, they're just referring to any generic ionic compound. Ionic compound and salt is synonymous with one another. And then water is, of course, just H2O. Okay, so this is an acid-base reaction here. Again, a special type of double displacement reaction that occurs in solution. Okay, so one of the things about these acid-base reactions that can make them a little bit tricky is the balancing of our acid-base reaction. Because we have hydrogens in this formula over here and in this formula over here combining to make water. In this particular case, you can convince yourself that everything's balanced. I have the same number of hydrogens on both sides, same number of chlorides, same number of sodiums, et cetera, et cetera. This is a particularly easy acid-base reaction. Everything's 1 to 1 to 1, all right? But one of the ways that we can sort of make these a little bit easier to balance is just to note that in these chemical reactions, when they're all balanced, the number of hydrogens in my acid are going to be equal to the number of hydroxides in my base, are going to be equal to the number of water molecules on the product side. All right, it's one hydrogen combining with one hydroxide to make that water molecule. So keeping this in mind for balancing our acid-base reactions can make life a little bit easier. Let's do a slightly more difficult one, and you guys are going to balance this chemical equation for me here. All right, now our acid is going to be sulfuric acid, H2SO4, plus KOH. Again, in order to get our products, we're going to swap those two cations, or swap these two things that are listed first in my formula, the potassium and the hydrogen. So now it's K2, whoops, that's not a 2, K2SO4 plus H2O. Okay, and if we're being good with our states of matter, these are all aqueous, but then water is a liquid. So here's an unbalanced acid-base reaction. Everybody take a second and balance that acid-base reaction. Okay, and what's going to make this a little bit tricky here, if we do it the long way, or our normal way, where we just count the number of hydrogens on both sides, what makes this tricky is that there are hydrogens in both of these formulas here. So as soon as I update the coefficient for one, it's going to change the number of hydrogens that are on that side. So again, for these acid-base reactions, I recognize I have an acid because hydrogen's listed first. I recognize I have a base because it's this salt with hydroxide in there. and I'm producing some ionic compound in water. I have an acid-base reaction on my hands. So instead, I'm going to look at the number of hydrogens that are in my acid. In this case, there are 2 hydrogens in my acid. Well, this has to be equal to the number of hydroxides that are in my base. Currently, there's only 1 in this chemical equation. And they're going to be equal to the number of waters. I also just have 1 in this chemical equation, right? So in order to balance this, I'm going to put a coefficient of 2 out front of my base. Now I have 2 hydroxides. All right, so the number of hydrogens equals the number of hydroxides. And I'm going to put a 2 out front of the water, because now my number of waters are equal to the number of hydroxides and hydrogens, right? So you could do it the long way. It's not like it doesn't work out. It's just if we remember this little trick here, it'll make our lives a little easier. These are kind of notoriously difficult, not dissimilar to our combustion problems, where we said we were going to save the high oxygens till the end, right? We had a little bit of a strategy to make our lives easier. Same thing with these acid-base reactions here. The number of hydrogens are always going to equal the number of hydroxides, which will also always equal the number of waters in my product. If I just want to be careful here and make sure that everything else is balanced, I see I have the same number of sulfurs on both sides and the same number of potassiums. I can convince myself hydrogens and oxygens are also the same, right? So this thing as is balanced here. Okay, so let's remind ourselves of our stoichiometry, as well as me, I guess, because it's early Monday morning here, all right? So now we're going to take this chemical reaction here and do a stoichiometry problem. So if 2.5 moles of H2SO4 are consumed, how many moles of H2O are produced? All right, so we got a mole stoichiometry problem on our hands. I'm going to give you all a head start here. Based on what we discussed last week, we should be able to do this stoichiometry problem here. We need to convert from our amount of sulfuric acid that we were given, H2SO4, into our amount of water. So we're going to need to use one of those stoichiometric ratios, right? That's how we do our math with our balanced chemical equation. So again, I'm going to give you all a little bit of a head start here. I'm given an initial amount of sulfuric acid, and it's asking me for the amount of water that's produced. And the only way that we can jump from one compound to another in our chemical equation is by building a stoichiometric ratio that we get from this balanced chemical equation. So for this particular one, it would be 1 mole of H2SO4 over 2 moles of water. 2 moles H2O, right? And the 1 comes from the fact that in my balanced chemical equation, I have 1 hydroxide ion and 2 water molecules, right? So that's where those numbers come from. And for any stoichiometric ratio, just like with any conversion factor, you can take it and flip it upside down. So 2 moles of water on top and 1 mole of H2SO4 on the bottom. So before I do anything, I know I'm going to need to use one of those two stoichiometric ratios because my problem starts me out in an amount of H2SO4 and asks me for an amount of a different compound in my balanced chemical equation, right? So that's how we jump from one compound to another in our balanced chemical equation, are these stoichiometric ratios here. All right, let me get rid of some of this color here. Okay, so then I'm going to start off my problem with my amount of my sulfuric acid, that 2.5 moles of H2SO4. And I'm going to multiply by one of these two conversion factors here. All right, and I'm going to pick the one that will allow me to cancel out the units that I don't want and enter into the units that I do want, right? So I'm trying to cancel out moles of H2SO4 and end in moles of water. So I'm going to multiply by that stoichiometric ratio on the right. All right, if I punch this into my calculator spits out 5. I got to do these last two steps that we always got to do when we do math in a chemistry class. I got to do my units, and again, you can check your units because everything should be set up in such a way that what you don't want, the moles of H2SO4 cancel out, and we're left with moles of water. And then what's that very last step that I got to do? Sig figs. All right, remember these mole ratios are exact. They do not limit your sig figs. So the only thing I'm going to pay attention to is my initial measurement here with these 2 sig figs. And so my final answer needs to have 2 sig figs as well. So not just 5, which is what my calculator spits out, but I'm going to report my final answer as 5.0. Awesome. Okay. So now we're going to take this same chemical equation here, and we're going to do a very similar problem. But in this particular one, what we did first, I told you that 2.5 moles of H2SO4 were consumed in this reaction, right? So then we just made this jump from H2SO4 to water, because I know if 2.5 moles of H2SO4 are consumed, and for every 1 mole of H2SO4, there's 2 moles of water that are produced, that's how I can do my stoichiometry problem. So now I'm going to take this same balanced chemical equation, and we're going to do something slightly different. These are what are called limiting reactant problems. Okay, so if 2.5 moles of H2SO4 are combined with 4.5 moles of KOH, how many moles of water are produced? All right, so let's take a step back and make sure we can see how this problem differs here. I'm still asking at the end of the day for moles of water, right? How many moles of water have formed here? But the difference is I'm not just giving you one starting quantity. You still have that 2.5 moles of H2SO4, but I'm not saying that's how much is consumed. I'm simply saying I'm going to combine that with a certain amount of KOH. All right, so I'm mixing these two together, and I want to know how much water is formed from that. Okay, this is what's called a limiting reactant problem. It turns out that one of these two reactants is going to get consumed first, and that's going to dictate how much product is actually formed in this reaction. All right, so before we solve this, let's just do a little bit of a simpler analogy here. Everything's a little bit more complicated when you're relating it to chemistry, to these teeny tiny little molecules that are hard to visualize because we've never actually seen them before. So let's do a similar sort of problem, but with something that we all know, which is making a sandwich here, all right? So we're all going to start a sandwich company, the Plain AF Sandwich Company, all right, where we only serve one thing on our menu, and it is a bland ham sandwich, okay? And this is how we're going to make our ham sandwich here. Here's our recipe. 1 slice of ham plus 2 pieces of bread will give us our 1 sandwich. All right, this is the only thing we're going to serve. It's $1 million idea here. All right, so if I have 4 slices of ham and 10 pieces of bread, how many sandwiches can I make? 4 slices of ham and 4 pieces of ham and 10 slices of bread. How many sandwiches am I going to get out of this combination here? 4. Only 4, right? I have enough bread to make 5 sandwiches, but I'm limited by the number of pieces of ham that I have, right? I'm starting to put these sandwiches together. I'm going to run out of ham before I run out of bread. Right? So the amount of product that I can get, the amount of sandwiches that I can get is limited by one of these 2 components here. Okay? So what if I had 4 slices of ham and 6 slices of bread? How many sandwiches can I make? I can only make 3 sandwiches. Right? Even though I have more bread than I have ham, in my sandwich recipe here, I have to use 2 slices of bread for every 1 slice of ham, right? So even though I'm starting out with more bread, in my recipe, it's a 2 to 1 here. So I'm still going to consume that bread when I'm putting this together before I consume my ham, all right? So we got to account for how much of each starting material we have, but also this stoichiometric ratio in which they're being consumed in our recipe, in our chemical reaction. All right, so going back to our chemistry problem here. Again, we have our 2 reactants. So we're going to have to do a limiting reactant problem here. Step 1, we're going to go from moles of H2SO4 into moles of our product, H2O. All right, so we're going to go from reactant 1 to product. That's the first calculation we're going to do here. All right, and for the sake of convenience, I kept the number the exact same as in our previous problem here. So we've already done this particular calculation, right? This was converting that 2.5 moles of sulfuric acid into moles of water. So that's how much water I could get if all of my sulfuric acid is consumed in this reaction, right? But again, I don't know how much is. I got to figure out which one of my reactants is limiting. So now we have to do a second calculation here, where we're going to go from moles of KOH into moles of water, right? So now I'm going to take that second reactant, reactant 2, and convert it into product. Okay, so given our balanced chemical equation and the text of our problem here, everybody take a second and perform this following calculation, converting from moles of KOH into moles of product. right, so now I'm going to start with my 4.5 moles of KOH. And I'm going to need to use that stoichiometric ratio from my balanced chemical equation that tells me that for every 2 moles of KOH that are consumed, 2 moles of water are produced. So if I punch that into my calculator, 4.5 times 2 divided by 2, get 4.5 moles of H2O. My sig figs and my units I kind of did quickly here, but yes, that will all work out to be 4.5 moles of water. All right, so we have to compare these two calculations here. Importantly, what this first calculation is saying is that if 2.5 moles of that first reactant, H2SO4, is consumed, then 5.0 moles of H2O would be produced. Right? That first calculation is telling me if every bit of that H2SO4 was consumed, how much water would be made. And my second reaction is saying if 4.5 moles of KOH are consumed, then 4.5 moles of water are produced. Okay, so how much water is actually going to get produced in this reaction here? The amount of water that's actually going to be produced is the 4.5 moles of water. My calculation is saying that I have enough sulfuric acid to make a full 5 moles of water, but I don't have that much KOH. My KOH is my limiting reactant here. It's going to get consumed, making only 4.5 moles of water, and I won't have enough left over. There's not going to be anything left over to make that total of 5 moles, right? So we're going to compare these two values here. We do these two calculations, and step 3 is to compare whatever the smaller value is. That tells me what my limiting reactant is. So I look at these two numbers here. I'm going to compare my 2 moles of water, my 4.5 to my 5.0. Whichever one of those two values is smaller tells me what my limiting reactant is. All right? So what is my limiting reactant in this reaction? Right? So importantly, it's not going to be this. Moles of water. Water is not going to be my limiting reactant. My reactant has to be on the reactant side. Right? So my smaller number tells me that my KOH is my limiting reactant. Right? Which one of my reactants is limiting here? So that smaller value tells me what my limiting reactant is. For this particular reaction, for this particular problem, I can say my limiting reactant, that's that KOH. The other one we call the excess reactant. So in this case, my excess reactant is that H2SO4. Okay? So the amount of water that's produced is going to depend only on that limiting reactant. Doesn't matter how much of the excess reactant we have, there's going to be a bunch of it left over, right? So what we can say is the amount of product, which in this case was water, is dependent only on your limiting reactant. Okay, so in this case, my amount of water that's produced is that 4.5 moles that I get from my limiting reactant. All right, so let's do another one here. We're going to roll together everything that we discussed here. First, our acid-base reaction. We're going to take HBr. We're going to mix it with barium hydroxide to produce barium bromide and water. Okay, so step one is to balance our chemical equation here. And now we have a limiting reactant problem here. I'm going to say that I'm going to combine 2.5 moles of that acid HBr with 2.5 moles of that base barium hydroxide. And I want to know how many moles of water are going to be performed at the end here. All right? So what I'm going to do is I'm going to give you all a bit of a head start here. I want you guys to work through as much of this problem as you can. First, start by balancing it. Then on doing your limiting reactant stoichiometry. I'm going to kind of quietly fill in the work up here after I give you guys a bit of a head start so that you can look up if you're stuck, and then we'll discuss the problem. All right, so I'm balancing my acid-base reaction here. The number of hydrogens has to equal the number of hydroxides. In my base, there are 2 of those OHs, right? That's why it's in parentheses with that little 2 outside there. How we indicate that we have more than one polyatomic ion, put it in parentheses. My acid only has 1 hydrogen, so I'm going to need to put that coefficient of 2 out front so that the number of hydrogens equals the number of hydroxides. All right? That also has to equal the number of water molecules, so I'm going to stick a 2 outside on my product side as well, so that again, number of hydrogens equals number of hydroxides equals number of waters. So now in my stoichiometry here, I'm going to first start with my first reactant, my moles of HBr, and convert that into product. So I use that stoichiometric ratio where 2 moles of HBr are consumed for every 2 moles of water are produced, right? That's how I got that term there. Take my initial amount of HBr, multiply it by my stoichiometric ratio. This would tell me that if my 2.5 moles of HBr were consumed, I would get a total of 2.5 moles of water as my product. But this is a limiting reactant calculation. So now I got to do another calculation, starting with my second reactant, my barium hydroxide. Now I'm going to convert from that 2.5 moles of barium hydroxide into moles of water using that stoichiometric ratio of 1 to 2 from my balanced chemical equation. So this is telling me that if all of that barium hydroxide was consumed, then I would make 5 moles of water. So when I mix these 2 together here, which one is going to be my limiting reactant? The HBr, right? So I'm going to compare these 2 values here. The smaller value indicates my limiting reactant. But again, reactant, so water's not a reactant. My limiting reactant here will be that HBr. And so then we would call barium hydroxide the excess reactant. Okay, and to finish off the problem here, the problem was asking me how many moles of water would be produced when I mix these 2 together. So how many moles of water am I going to make with this combination? That limiting reactant tells me how much product I can actually get, right? My HBr is going to be consumed first after only 2.5 moles of H2O are produced. Okay? So these limiting reactant problems, you got to do 2 calculations and then compare those answers. That'll tell you what your limiting reactant is and your excess reactant. And the amount of product that you get is going to be dependent on that limiting reactant. Just like the amount of sandwiches that we could make were depending on which one of these was going to be consumed first. It's the same idea, but using chemicals instead of ingredients. Okay? So now we could continue this. Now that we've done all this work figuring out what the limiting and the excess reactant is, there's a few more things that I can ask you about this system here, in particular with regard to that excess reactant. Okay, so using this same problem here, our 2.5 moles of HBr combined with our 2.5 moles of barium hydroxide. We've established that 2.5 moles of water are going to be consumed in this, are going to be produced in this reaction. All right? But now I could ask you how much of that excess reactant is consumed. Okay, we've already established that our limiting reactant is the HBr and our excess reactant is the barium hydroxide, right? How much of that limiting reactant is consumed in our reaction? We said that HBr was our limiting reactant. How much of that 2.5 moles of HBr is consumed in this reaction? If I'm limited, all right, let's go back to our sandwich here. When I made these 4 sandwiches and I was limited by the amount of ham that I had, how many slices of ham did I use making these sandwiches? I don't know what the hell just happened out there. All of it, right? You use all of your limiting reactant. That's what it means to be limiting, is that it's going to be used up first. So if I ask you how much of the limiting reactant is consumed, that's the easiest thing I could ask you because the answer is just all of it. All 2.5 moles of that HBr are going to be consumed. Okay? If I ask you how much of the excess reactant is consumed, now all of a sudden we got to do some math because the only thing I know from my calculation here is that it is not all 2.5 moles, right? This is an excess, so there's going to be some left over. So how much was actually consumed? We're going to have to do another calculation here. This time we're going to go from our limiting reactant to our excess reactant. Right? What I do know is that all 2.5 moles of that limiting reactant, that HBr, are consumed in this reaction. I need to do some stoichiometry here, jumping from my limiting reactant into my excess reactant to figure out how much of that was consumed. All right? So for the sake of convenience, I'm going to bring down this balanced chemical equation. Again, we said that HBr was limiting and that the barium hydroxide was excess. And again, you're going to do a calculation here where you jump from the amount of limiting reactant into the amount of excess reactant using our stoichiometry. All right, so everybody take a second, build that stoichiometric ratio and jump from the amount of limiting reactant, HBr, into units of that excess reactant here. All right, so starting out with our limiting reactant, that 2.5 moles of HBr, we're going to use our stoichiometric ratio to jump from HBr into barium hydroxide. My balanced chemical equation tells me that there's a 2-to-1 ratio here. There are 2 moles of HBr consumed for every 1 mole of barium hydroxide that's consumed. All right, so using that stoichiometric ratio, I see that in this reaction, only half of that barium hydroxide, 1.25 moles of barium hydroxide, are consumed. Right, I got to round this to the correct number of sig figs here, so I would report my final answer as 1.3 moles of barium hydroxide, and I'm going to even say is consumed, so we don't get confused here. Right, so that's the first thing that I could ask you is how much of that excess reactant is consumed in this reaction, right? Again, we know from our calculation that that barium hydroxide was in excess, so not all of it was going to be consumed, right? So that's what we were just calculating here. How much of it gets consumed? Okay, the second thing that I could ask you about that excess reactant is a very similar quantity here, but how much excess reactant remains? Because again, not all of it's going to get used up here. So I could ask, how much of it is left over at the end of the day then? All right, so how much of that excess reactant remains? Well, let's think about this here. we know that at the beginning of the day, we started out with 2.5 moles of that barium hydroxide in our mixture. And then we just calculated that this 1.25, or rounded to the correct number of sig figs, 1.3, is consumed in our reaction. So then how much is left over? The difference between the two, absolutely, right? So how are we going to get the excess reactant remaining? We're going to take our initial amount and we're going to subtract the amount that's consumed. That will give us the amount that remains in solution. Now, it's going to make these particularly big pain in the butt is that now we're not doing multiplication division, we're doing addition subtraction, right? We got to remember our addition subtraction sig fig rules, okay? The other important thing is you're always going to use the unrounded value from your previous calculation in your math here. So I'm going to take my 2.5 moles of barium hydroxide. That was the initial amount that I had. And I'm going to subtract that 1.25 moles that are consumed. All right, it just so happens that my sig figs here line up well. All right, so in this case, I know based on the position of these two numbers that I'm going to be rounding to that 10th place. And so this tells me how many moles of my barium hydroxide remain at the end of this reaction. Just be good and put barium hydroxide. All right, and it just turns out that it's the same value as the amount consumed because it was half of our initial, but rounded to our correct number of sig figs, 1.3 moles. That's how much remains. All right, so we introduced this new type of reaction here, these acid-base reactions, and we used it to illustrate this new type of stoichiometry problem here, these limiting reactant problems, where you got to calculate how much of your reactants are consumed in order to figure out which one's limiting. That'll tell you how much product you get. Cool.